Hi, everybody. I'm Nicholas. I am a undergraduate researcher at Rice and also now working with ThirdAI. And today we're just going to be talking about some of the research and stuff we've been working on with using deep learning on commodity hardware and how we can do software accelerations to train huge deep learning models efficiently on CPUs. So kind of the agenda for today, we're going to start off, we're going to talk about the current state-of-the-art in machine learning, and we're going to talk about the limitations of that state-of-the-art, particularly with GPUs and training. And then we're going to switch a little bit, and we're going to talk about hashing and LSH, which is locality-sensitive hashing. Some of you may have heard of that, but we're going to go over that anyway. And then we're going to show how that can be applied to software acceleration for machine learning using this, borrowing techniques from neuroscience called sparse coding. Then we're going to do a demo of this, and then also share some of the other results we have using these techniques. And then we'll give time to answer questions and stuff in between. And they asked if you are asking questions, if you could come up and use the microphone so that it gets recorded. Okay, so the current landscape of AI. So in 2017, there's a quote from Google talking about how, for them, large model capacity is crucial because we have these huge training corpuses. We have all this text, we have all this data that's being aggregated from the internet, and we want to be able to train models on that. And in order to kind of capture that complexity, we need these larger models. And they're talking about how the goal is to train, get to a trillion parameter language model. And so since then, and this is still not complete because this only goes up to 2020, we can see this huge increase in the sizes of models. And so you can see here 1,000, so very quickly we eclipse billion parameters. And then we're on this kind of exponential track where in just a few years we're going from parameters that are 94 million to 17,000 in just a few short years. And even then, since then, even more recently, we have GPT-2, which is 1.5 billion parameters, G-Shard, which is from Google, 600 billion parameters. And then just the next year after GPT-2, we have GPT-3, which is 175 billion parameters. So we see it's a phenomenal increase, 100 times larger model in just a year. And then now we're starting to see those trillion parameter models. For example, the switch transformers, that is Google. There's a trillion parameter language model from Google. So they got to what they wanted. And then Facebook has a 12 trillion parameter recommendation model. And these are just this year. And so we can see that we've very quickly, if you look back, just from the last few years, we're going from measuring model sizes in millions to billions, and now we're already at trillions. And then the other thing that we're starting to see is that there's these new techniques in what kind of models we're using. So at one point, the state of the art for language modeling was all about RNNs, LSTMs, GRUs, and now we're seeing that the power of things like attention. And then there's other things for image processing. Convolutions are obviously still a lot of the state of the art, but there's interesting results that show that you can use patch embeddings to also get very good results. And then even more recently, we're seeing that attention, there's even alternatives to attention that use more MLPs. And just a couple of papers here that discuss that more in deep detail. And then even today, one of the biggest classes of models that are being used most widely are recommendation systems. And for example, Facebook's DLRM and Amazon's DSSM are largely based on MLPs. And so the next thing we kind of run into is, so we have these trillion parameter models and they're very powerful, but what is the cost of these? And how do we train them efficiently? And so currently the state of the art, as many of you probably know, is these models are trained on GPUs because you can have an incredibly high throughput for matrix computations. You can look at especially this graph here, comparing CPUs to GPUs. It very quickly, you completely blow away the throughput. And that's important when you have 12 trillion parameters that you need to train. However, there's a downside to this. They're not just a complete win. Each one of these GPUs can cost upwards of $10,000, and they only have 40 gigabytes of memory. Some of the newer ones have 80, but that's still very small when you think that you have 12 trillion parameters. You need multiple GPUs for that. GPT-3, which we talked about, I kind of mentioned earlier, cost $12 million to train. And if you look at it, yeah, so 175 billion parameters, and that it comes out to be around like 350 gigabytes of memory. And so then, so basically to train these models, you have to have a really high investment in these GPU clusters. And then once you have them, they're very good for these machine learning workflows, but they're very different than what you'd be used if your company is using them for like lots of other servers or web servers and stuff. You have like a completely different like tech stack just for training these models on top of the heavy investment. And they're also different than the hardware you might already have. And then, yeah, so then there's, one of the things we're also starting to see is like, and you can look at the carbon footprint too. And we have this nice chart here, and you can see how basically that's the other way of looking at it, not just the cost side, but also the environmental impact of these models. It takes a huge amount of energy, it consumes a huge amount of resources to train these things. I guess as a first stop, if there are any questions, most of this is probably stuff you guys have heard, but okay. So I guess the next thing we want to talk about is like, so what else can we do? Like, what are the alternatives we have? Because obviously these are these hugely expensive models. So this is, we're going to switch up and talk about hashing in LSH.
Okay, so having seen all the limitations of GPU-based, this traditional GPU-based models, we can see that there's a need for a new way to train those models. And so today we're going to talk about hashing, a simple and powerful tool. So what comes to your mind when I say the word hash? Maybe a hash table, or maybe a Java hash map. Well, in fact, if you have already used a Java hash map before, you've already worked with hashing. So what exactly is hashing? Well, basically, hashing is another way of saying, give me a number associated with an object. And this object can be anything. It can be an integer, a real number, a vector, or an image. And the tool to generate this number is a hash function. More specifically, a hash function takes in an object x and maps it to a number to another number within a specific range. And since it is a mathematical function, it must have this property where the same object always gets mapped to the same value. Well, sometimes we also want to impose some more interesting properties to a hash function. Sometimes we want different objects to be always mapped to a different value. Well, this is not guaranteed for all kinds of functions. That's why we give it a special name. We call it a perfect hash functions. And we'll see how powerful or how useful they can be in just a bit. Now, this is basically it for a definition of a hash function. Well, how do we use it? Let me start by giving you a small task or a small question that's frequently asked in some of the tech interviews, or it comes in handy in many situations. So say you have an array of integers and you want to remove all duplicates in this array. What are the methods? What can you do? Well, we can, intuitively, we can find all pairs in this array and compare all pairs of integers in this array and remove the duplicates as we see it. How many pairs are in this array? Well, to be exact, it's n times n minus 1, n times n minus 1 over 2. So it's on the order of n squared, which is very inefficient. Well, then we can do sorting, right? We can sort this array, and after you sort it, all the elements, all the duplicates will be grouped together, and then you can do one pass over the array and remove duplicates on the run. And how does that take? It takes all of n log n, depending on the sorting algorithm that we use. Well, now I'm saying that if we use a hashing-based method, we would only take a linear time, all of n. How does that work? Let me show you with a quick demo right here. Say we have this array of integers. It's very short. So how does hashing find the duplicates in this array? Okay. Say we have a simple hash function that maps an integer to another integer. And it satisfies just this simple property of any mass functions. Now what we do is we will initialize an array of empty buckets or empty sets, just an empty groups if you want. And this array has the length equal to the range of the hash function that we just provided. And how does the hash value relate to this array? Well, the hash value will be the index that we use to access each bucket in this array. So, for example, if 40 gets mapped to 0, and then we'll insert 40 into the bucket with index 0. That's what we're going to do right now. So we insert 40. 40 gets the index 0, insert into the first bucket. 51 gets hash value of 2. So we insert it into the third bucket, so on. We do for 32. We do for 1033, 14, 67. 67 has the same hash value as 51, so we insert them into the same bucket. Now comes the interesting part. We see 1033 again. Since we have this property, the same object will be always mapped to the same value. So it will go to the fourth bucket, and guess what? The fourth bucket has just one value, 1033. We found it. We found the duplicate. So, well, convince yourself that this algorithm does take just a linear time complexity. Now let's take a step back and look at what we just did. Look at this hash function. Well, if we look at it from a mathematical point of view, well, it might be not that interesting because, well, we've studied mathematical functions for centuries, right? It seems like it's just a function, sometimes injective, sometimes bijective. Why is it interesting? Well, let's change our point of view and look at it from a computer science point of view. From a computer scientist perspective, what we're really using is direct memory access. We're using the fact that direct memory access is super fast, and it takes negligible time in a modern computer. For example, let's look again at what we just did. What we really did is, for each number in this array, we map it to an index in this array, and we access the bucket in this array. And in accessing that, it's super fast, right? So that's the takeaway here for hash function. What we're really doing is, instead of sorting, instead of comparing, we're changing it into a memory access. We're accessing memory. So just how fast can this get? Let's see some statistics from a real-world program written in Python. Okay. So here, this is a slightly more complicated example than I just showed, but it's basically the same. So here we have two arrays. Each has the size of 15,000. So we have a total of 30,000 elements. And this array stores strings instead of integers. And right now we want to find all the duplicates in this 30,000 elements, in this set of 30,000 strings. So we'll first do a comparison-based method. We're comparing every pair of elements, every pair of strings in this database, and how much time does it take? Let's see. Well, I can't run it right now. So, well, the number doesn't show up on the Google Colab, but well, if you want to run it yourself, we're happy to share the code with every one of you. But, well, I've just run it last night, and I still have the number in my head. So, well, I'm counting on you to trust me. But, so here's the number. So here's the stats. If we're doing comparison on every pair of strings in this database, it takes 6.978 seconds. That's almost 7 seconds to look at every pair. And what if we do hashing? What if we do hashing, right? What we do is we build a hash table, just like what we just did, this array of buckets. And then we would need a hash function, right? How should we design a hash function? Well, this hash function must achieve two things. First, it will map a string into an integer. Second, it should be as perfect as possible. That is, we don't want it to map 20,000 elements into one bucket and the rest into another bucket. We want each bucket to be distributed enough. And so let's look at the first property. How can we map a string to an integer? Well, we know that every letter has an ASCII code related to it, right? So why don't we take a string, take all the ASCII codes of the letters and sum it up? Well, let's give it a shot. Here's our hash function. And so here, we run it, and well, guess how much time it takes? It takes 0.14 seconds for the whole thing. Compared to 7 seconds, this is 50 times faster than doing comparisons. Well, what if I have a better hash function? So now instead of designing my own hash function, I will use a famously useful hash function for strings called murmur hash. Well, the introduction about murmur hash is widely available on the internet. I'm not gonna explain the mechanism behind murmur hash right here. But using murmur hash, it's simply better than the hash function that I just designed. And in fact, if we just change gear, switch the hash function we use into murmur hash, the total time it takes is, again, I'm trusting you I'm counting on you to trust me. The total time it takes is 0.09 seconds, which is a 1.5 times speed up than the previous hash function we used. Now we times that with 50. That is a total of 75x speed up compared to just doing comparisons. And yes, that is the demo. And I hope that you can all go back and run it. So at this point, are there any questions regarding to hash functions? Well, so the question is, the question is, if you say if you have a map or a Python dictionary, you would have a fixed hash function, right? And then you insert, like, let's say in Python, you insert one element, it will be, insert a string. It will go through this hash function, gets its hash code, and will be stored in that dictionary. And if you have another object, well, a hash function will take, like, it has a domain. It can take in a lot of objects, not just one. So if you have strings, then this hash function can take in like any kind of strings and give it a hash code. So in your question, if we're inserting another string or just another integer, it will be still valid in the domain of this hash function, and it will still give a hash code within the defined range of this hash function. Does that answer your question? Sort of? No. It's, oh, I see what you're saying. Oh, so I see what you're saying. So So yes, the hash value is not like the key value pair, the value in the key value pair in this Python dictionary. So the value, you will define the value, right? But when you are storing the key, you're not storing like the string. In a hash table, you're not storing the string, you're storing the index. So the hash value will be the index. Yes, say if you want to give the letter A a value of 20, and the hash value of A would be like 1,000, then what you'll be storing is at index 1,000, there's a value of 20. Does that answer your question? Okay, awesome. Okay, so now we'll present a slightly more complicated but much more interesting question. What if we want to, instead of duplicate detection, what if we want near duplicate detection? For example, what if we want 1.001 to be a duplicate of 1, but 1.9 to be a duplicate of 2 instead of 1? And this will come in particularly handy, for example, in neural networks. In neural networks, we would want to somehow group similar neurons that fire together. So in this simple example here, we could design a hash function like this. If a number is within a 0.5 difference from another number, from another integer, we'll give it a floor. Otherwise, we'll give it a ceiling. Well, here's another question. Does this mean that a near duplicate detecting hash function has this property, that the hash value of x plus delta is always equal to x with the small value of delta? No. The answer is no. We cannot guarantee that. Because if this is guaranteed, then we'll have x plus 2 delta, x plus 3 delta, and they'll all eventually map to the same thing as x. And then we don't have near duplicates. Everything is a duplicate. That is not what we want. But there's a way out of it. And I will hand it over to my colleague, Alan, right here, to talk about the powerful locality-sensitive hashing.
All right. Just making sure, did everyone get the link to the previous demo? And here it is if you want to take a look. All right. So let's start talking about locality-sensitive hashing. So imagine you are currently a Facebook engineer, and you have been assigned the task to filter out and sort of block all the content related to this minion image. And you want to filter it out for all the database images inside of Facebook. And you have one example, which is just that minion image. And we want to find all similar minion images from Facebook's database of potentially over 250 billion images. So you can imagine how large that scale is. And each image can easily exceed over 1 megabyte. And if we wanted to use brute force search, that would take over at least 10,000 terabytes of memory to compare images on disk, which is quite an impossible task for a regular laptop or a PC. And even large clusters out there don't have the memory capacity to do that. How about another problem? So another problem is that we often bring up is search engines related to real-time search. So if you're now suddenly a Google engineer and you wanted to perform autocorrect on user search queries, you'll have to compare that query with a database of over 50 million past queries, potentially, to find the most similar ones. So you can also imagine how difficult brute force would be for this. On a regular CPU, it might take over 5 minutes, but in reality, we only have a couple of milliseconds to work with before the user becomes bored and either types out their query fully or just goes to another search engine. So ultimately, how do we make this faster? And the hard reality is there's not really a fast way to find exact near neighbor search. What about, let's not actually care about an exact solution, right? What if we're okay with just having 98% recall? So only just like a couple of similar strings, a couple of similar queries are missing from that dropdown, right? So in this case, we can just use an approximation. And there's been a lot of research done before about approximate near neighbor search. And what we will talk about further is sort of a more efficient and both time-wise as well as space-wise efficient approach to approximately solve this problem. And the good news is that anyone with a laptop can easily try out this method, and you don't need a supercomputer to do that. Okay, so coming back to what Henry said about the near duplicate problem. So previously, each item X was associated with its own respective memory location at H of X. So these hash functions were deterministic, right? So what if we want near duplicates to be hashed to the same memory location? We might come up with a simple relationship like the one here. H of X equals H of X plus 0.001 for all X. And we also talked about how this was a problem, right? Because ultimately, it would just degenerate to the identity function. So, as a result, we should not use deterministic hash functions to solve our problem. And instead, we can add randomization, probabilistic methods. So consider this new hash function relation. H of X equals the ceiling function of 100x plus a random pre-generated random number between 0 and 1. So I claim that H of X equals H of X plus 0.001 with a 90% probability. And how does that work? So how do we confirm that? Well, you can just plug in a simple example, right? X equals 1 and X equals 1.001. We can plug that in, and we get that H of X is equivalent for both of those X's as long as this random number between 0 and 1 is less than 0.9, so 90% chance, right? And furthermore, we can say that most of the time, these are hashed to, these have the same hash values. And also most of the time, if X and Y are arbitrary, then the hash values are most likely not the same. So we can avoid some collisions in that sense. Okay, so locality-sensitive hashing is pretty much the concept that we use to approximately solve the nearest neighbor search problem. And we can see that while the normal hash function maps all of these points to its own respective bucket here, collision bucket, the LSH functions, on the other hand, map only the similar points together. So, for example, the red points here are only mapped to this one bucket, but the red points are mapped to any arbitrary bucket here. So how do we turn these LSH tables into an algorithm for searching for nearest neighbors? The first idea is that we can actually concatenate hash functions together, LSH functions together. So say, for example, we have two LSH functions, H1 and H2. And if we were to just use H1, we might actually just find too many undesired collisions. So what does undesired mean? It means that two very dissimilar objects, X and Y, could potentially be hashed to the same bucket. And we don't want that, right? We want to maintain the property that only similar objects are hashed together. So what if we want to leverage more hash functions? And this is where H2 comes along, right? We can use H2, another LSH function, to sort of boost the quality of this bucket and make sure that we only have desired collisions, where only the red points that you saw in the previous slide were hashed together to the same bucket. And obviously, this can be generalized to include multiple hash functions, k of them specifically, for each table. So h of 1 to h of k. And the second idea is that we can improve the recall. What does that mean? Improve the probability that similar objects are indeed hashed to the same bucket, and decrease the probability that there might be a near neighbor, a similar object, that was missed. So to do so, we can create multiple tables, and each hash table has its own set of k hash functions, k independent hash functions. And we can hash each of the database objects that we have into all of the L hash tables, and then we'll have L buckets to work with. L buckets of similar objects to work with. So, for example, if one similar object was not hashed to the same bucket in table 1, it might have been hashed to the same bucket in table 2. If it wasn't, then we look at table 3, and so on, right? So to summarize, increasing k, increasing the number of LSH functions that we use, controls the quality of the buckets for similar objects, while increasing L, which is the number of hash tables, improves our recall and decreases the failure probability of near neighbors not being in any of our similar buckets. So we talked about hash table buckets quite a bit, but ultimately, how do these help us with the near neighbor problem, right? And the short answer is this significantly improves our querying process. So for example, this magenta point Q right here, if we were to hash that single query point, we might get these set of hash values. 0, 1 concatenated with 1, 1 is 0, 1, 1, 1. And let's say this bucket right here was also 0, 1, 1, 1, right? Because the red points are similar color to the magenta point of our query. And as it turns out, we actually have a perfect set of near neighbors to work with, perfect set of candidates of near neighbors. And instead of a brute force comparison, we instead only need to compare this magenta point with only those 3 points. So a brute force would compare this one single point with all 20 points, whereas with LSH, we only need to compare this one single point with these 3 points. So that's a pretty significant improvement, right? And if we have L hash tables, then we would hash Q into all of the hash tables, all of the L hash tables, and get L buckets to work with, right? And we can take the union of those buckets to get our complete set of candidates. So let's formulate an algorithm. And most of this I've already talked about before. Pre-processing, we choose K and L. So K is the number of LSH functions, L is the number of LSH tables. We can create L hash tables, LSH hash tables, and for each of those hash tables, we have K independent LSH functions. So in total, there would be K times L pre-generated LSH functions. And lastly, we can insert every single point from our database into all of the L hash tables. So for querying, it's the exact same process, right? We determine the bucket location of that query in each of our hash tables, and take a union of all its buckets, and then get the best set of neighbors to use for our nearest neighbor search. So what about these LSH functions? We haven't really talked about them too much yet. I don't think I'll talk about them too much today, unfortunately. If you're interested, you can feel free to look them up. They are also in the demo, MinHash specifically, so if you want to take a look at that even more, feel free to. So MinHash, they have this property that the probability of 2 min hashes is actually equivalent to what we call the Jacquard similarity, which is a common similarity metric that we use. And there are other LSH functions, including signed random projections, SRP, which is based off of cosine similarity, bit sampling, which is based off of Hamming distance, and semantic hashing, which uses hash codes from a neural network. Okay, and this is the same link as the hashing demo. It's just at the very bottom. So I guess I can talk about it if, Nick, you want to come up and screen share. Yeah, you'll have to sign in to actually like run the code in the demo. Okay, so these are just some helper functions that we use to calculate n-grams. And n-grams are what we use for min-hash on strings. So min-hash, that's good. And below here is the LSH, a pretty simple LSH class, and you can take a look at how the implementation is done for the hash tables, the LSH tables that we talked about. Also in this class are lookup functions. Oops, sorry. Let me just make sure I ran that. Yes. Our lookup, a lookup function to perform the querying process, and an insertion function to insert all of our elements from our database into the LSH hash tables. So below here is just a toy example that you guys can run, which inserts all of the 10,000 most common English words into the LSH tables. And here we can generate some queries with some typos, right? So ACC has a typo WCC, acceptable, I don't know how to pronounce that, but that's obviously a typo, right? So those are the queries that we want to use. And we can also create our LSH object here. And feel free to change these values if you want to. K is the number of hash functions, 50L is the number of hash tables, and R is the number of bits that we want to use for our bit range. So it takes 15 seconds to insert about 10,000 strings. And keep it in mind that this is in Python, so it's slightly slower. So right here is a brute force comparison for 100 queries. So we're calculating the Jacquard similarity between each query string, 100 query strings, and all of the strings from our database. So that takes 5 seconds. And LSH-based comparison for 100 queries on all of the similar words from the bucket only takes us about 0.3 seconds. So this section right here calculates the average Jacquard similarity for a random query. And you can see here that the Jacquard similarity for LSH-based comparisons are much higher than the brute force solution. So our bucket of candidates was a pretty good bucket. And below here is something that you can also try out. Feel free to replace the replace me string here for a user specified query, and it'll show you the top 10 near neighbors that we got from our union of all the L buckets. Yeah. So if I type in something like doctor instead of doctor. So the first one was actually actor because the D was extra. They thought the D was extra. But we also got doctor here, which is pretty cool. Okay, I think that should be about it. I'm going to move it on to Nick for talking about how locality sensitive hashing sort of is used for our talk. Yes.
Okay, so just one thing just to touch on real quickly. So coming back, so earlier we talked about some of the costs and limitations of GPUs, and just to kind of add on to that to help kind of motivate this next section. So I guess a lot of you, especially if you have a computer science background, have heard of Moore's law, which is basically when we were sort of starting to build all these chips and computers. they kind of coined this phrase, and it describes that the number of transistors in a chip roughly doubles every 2 years. And for a long time we saw this. It's starting to slow now just because we're reaching like the physical limits of what we can do. But what we're starting to see is this new thing we call Huang's law, and that's named after the CEO of NVIDIA. And it's that the performance of AI doubles every 2 years. But not only this, but what's interesting about this compared to Moore's law is purely a hardware thing. It's saying we're going to get more transistors in our chips, we're going to have more computing power. This is saying we're going to get more better performance, but that performance is going to come both from advances in software and hardware. And so just to kind of foreshadow this a little bit, we're going to be talking about the software side of that. And this is also just a screenshot from a New York Times article talking about this too. And so we obviously talked about GPU clusters, but what about CPU clusters? Well, CPU clusters are actually really useful because they're relatively inexpensive. You can get them for like a fraction of the cost. Here's like an example, like 10 times less to get CPUs versus GPUs. They're easy to scale, and they're really versatile. You can have a CPU cluster, you can use it for all sorts of types of workflows. GPUs are much more specific. And the other thing too, as we mentioned earlier, the problems with GPUs is even top tier GPUs, you have 40 to 80 gigabytes of memory, which isn't a lot when your machine learning model takes up hundreds of gigabytes of memory. Well, you can easily get a CPU machine with a terabyte of RAM, so 1,000 gigabytes. And so we don't run into the same memory band issues with CPUs that we do with GPUs. Really, the only thing that we run into is something we talked about earlier, which is just that CPUs can't match the same throughput that GPUs can for machine learning workflows, at least for now. I guess, are there any questions about that? Okay. So this kind of brings us to our next big section, which is really like the crux of this talk, which is what can we do with neural networks? How can we re-examine them to see how we can use CPUs to train them efficiently and even come close to GPU levels of performance? Because that would be big, because there's a lot of benefits for GPUs. Like if we could train these models efficiently on CPUs, we could have cheaper clusters to train them. We could have bigger models because we don't have the same memory issues. So there'd be a lot of benefits to this. So as a quick review, I'm guessing a lot of you have seen this, some of you may not have. So the basic architecture of like the most like simple kind of classic kind of neural network you see is these like fully connected networks. And so basically you have these neurons, and then they're arranged in these layers, and there's connections between all the neurons between each layer. And the idea is you have some input, and each one of these connections is called like a weight, and it has some value, and you multiply like this input by this weight, this input by this weight, etc., and you sum those together, and you get like what's called like the activation for this neuron. You repeat that for all the neurons, and you go through the network. And then once you get to the end, you can use like some linear algebra and multivariable calculus. You can take the gradient, and you can use that to kind of minimize some sort of objective function, like usually called like the loss or the cost function. To kind of make that a little more formalized, if we say that these here are like x1 through xk, and we have for a given neuron here, we have W1, W2, all the way through WK. So we have all these components of the weight vector. Well, then its activation for this neuron n is just the sum of all of this product, and then this bias term at the end, which is kind of like, if you think about it in a neuron, kind of adjusts almost like the firing threshold, because this is all kind of takes inspiration from neuroscience. This thing F, it's not super important for the context of this talk, but just for the sake of like making this correct, it's kind of like a non-linearity. The reason for that is that otherwise this is just a linear transformation on the input, and so you could only ever learn a linear correspondence between the input and output. You add this non-linearity, which is some sort of like curvy function, and then suddenly you can approximate much more complicated things with your neural network. We can also represent it this way, which is more of like a vector dot product plus a bias. And then we can take it even one step further, and we can represent it as a matrix times the input plus a bias vector. And the reason I'm going into this detail is this is going to come up a little bit later. Remembering this kind of equation is pretty useful. And so this is just to compute the activation for any neuron. And you can apply that to any of these neurons or these neurons. So with that in mind, what can we do to make this training more efficient on CPUs? So to kind of motivate this, because what's cool about neural networks is a lot of the kind of core concepts come from neuroscience. So there's this idea in neuroscience called sparse coding. And the idea is that if you have some sensory input, you're going to have like a smaller number of neurons that are more influential and have like are highly active and for a given input, rather than having like a ton of like moderately active neurons. And so that's kind of an example here is like this image. This is like the idea like dense coding, where you have like all these neurons are kind of active, and this is the idea with sparse coding, where you see the same image, but you only have like a few neurons that are highly active. And so the kind of question we ask is there an analogy for this in neural networks? Can we do the same thing where for a given input, there's going to be some neurons that are highly active and a bunch of neurons that are only moderately active? And so I guess kind of an example of this, so say we have this image of this cute cat. Well, we see maybe like, so well, maybe only these neurons are active, and we get to this one here indicating that it's a cat. Or and then maybe for this funny looking dog, these neurons are active. And there's some overlap, but there's also some differences. And then we get to this here, which means it's a dog. And why is this of interest? Well, right now when we do this neural networks, what make it expensive is we're trying to compute all of these activations and do all of these matrix multiplications to kind of go from this input to the output of the neural network. And then the same thing in reverse when we're trying to compute, like when we're trying to learn the model and optimize it. But if only these neurons are influential, why are we computing all of these like neurons that don't have as much an effect on the output? And then if for those of you who know more, like there's one of the common nonlinearities we use is called ReLU. And that just kind of truncates everything that's all the neurons that have activation less than 0 and gets rid of them. So for example, if we have a really small activation, it's just going to get discarded anyway. So why did we compute it in the first place? And so that's kind of the motivating idea here, is that we have all these neurons, but for a given input, only some of them are more important. And if we had a magical oracle where we could say like, Oracle, what are the neurons that are most important? And it would say these neurons. And we just computed those neurons, we could still get a good result, but with much less computation. So that's kind of the idea. So really the thing we're missing here is we need a magical oracle. So if we recall, this is the formula I said would come back up. A neuron is most active when this is the largest. Well, this is just a dot product here. So when a dot product is large enough is when, because you can think of a dot product kind of like a projection, that's largest when those two vectors are similar and pointing in the same direction. So basically, to find which neurons are largest for a given input, we want to find which weight vectors are most similar to that input. And this is where it comes back to what we talked about earlier, which is locality-sensitive hashing. So we don't have a magical oracle that can tell us which neurons are most important, but we do have locality-sensitive hashing, and that's still pretty good. And it's actually good enough for what we need to do. And just kind of an analogy, if it helps think about it, is like when you do a web search, you don't look over the entire internet. You use like, they have indexes, they have tricks, they use a lot of other machine learning models to find like relevant results, and they just show those to you. And so it's the same kind of analogy is, for a given input, we're just trying to find the neurons that are relevant for that input, instead of just saying, okay, let's just look at all the neurons, and then only some of them will end up being important, but that's just okay, we'll just compute all of them anyway. Here we're saying, well, actually, we can do something smarter. We can say, these neurons are more important, so we're just going to compute them, and that's going to be sufficient. So we're going to kind of, for this is kind of like locality-sensitive hashing-based adaptive sampling in neural networks. And so we kind of have an algorithm that does this. So the first thing we do is we initialize our neural network, and then we take all these weight vectors. So I'm just numbering like these neurons 1, 2, 3, 4, 5, so they each have a corresponding weight vectors. We hash those weight vectors using locality-sensitive hashing, and we store those neuron IDs in a hash table. We can do that for all the layers of interest. We can do it for just one layer. This example just shows both. And the next thing we do, so we get some input vector here. We hash this input vector using the same hash function we used on these weight vectors, and we look up this hash table. And we say, okay, we have an input. We have these weight vectors. Which weight vectors are most similar to this input? And it's going to say, for example, 1, 2, and 5. So now here's our magical oracle, or LSH function, telling us that these neurons have weight vectors that are most similar to this input, and hence are most likely to have the largest activation. So we're just going to compute those activations, and we're going to ignore the rest, because we're saying that based on our LSH function, they're probably not going to have very high activations, and so they're not going to be as important for the final output. And then we can go into the next layer. And we can take these activations as our input to the next layer, and we can hash them too. And we can get a different set of active neurons that we say are like going to be the largest given this input from the previous layer. And so we can just compute those activations. So in this case, only 1 in 3. And you can see here too in this diagram, so we started off, and you can look at all of these weight vectors and all these connections, all these connections between all the neurons. And then already, so this is what we get to. Then we can compute the outputs for the final layer. And look how many fewer connections there are. So all of those things, so this is what's left that we actually need to compute. We can ignore everything else. So that's a huge savings. And this is kind of a toy example. In reality, we end up finding that we can get even higher degrees of sparsity, like we can only need to compute like 1% of the neurons. But for the sake of this even, it's really clear to see like the computations that you can save. So yeah, we compute the activations for the final layer. And then the last thing we do is we need to optimize our neural network. So we need to compute some errors and loss. We need to back propagate through the network. And we need to update all of the parameters using like gradient descent or something. And then the other thing we get is that we don't need to do this for all the neurons. We only used these neurons, and so we only have to back propagate through those neurons and their weight vectors. We can ignore all the other ones. And so that kind of gives us our algorithm. And I guess there's one other part to this, which is just that periodically you need to re-update the hash tables just because over time your parameters will change. And so what weight vectors might be similar to an input at the beginning of training, halfway through training might be slightly different just because you've learned different weight vectors. But other than that, this is kind of the algorithm we're thinking of. Are there any questions about this? Yes. Yeah. So I guess the first question, I'm not sure I'm 100% understanding. So for this, we're just looking at like a simple, like fully connected neural network where you have like one layer, you have just a series of layers that are only connected to the previous layers, and we're just feeding input through sequentially. And so we're not looking at any like sort of like residual skip connections or anything like that for this. Though obviously that's like a potential extension to this. This is just like for the sake of simplicity, explaining like a simple example. In terms of applications, so that's a really great question. We're gonna kind of talk about that a little more at the end, but I guess a sneak peek, there's lots, basically this can be used, this technique works on, well, I mean, this is a trivial example, but like simple feed-forward neural networks, and also some more complicated models. And you can use it essentially as an accelerator for machine learning, because you can use this same algorithm, we can apply it like a larger scale, and we can see really great speed ups. And we actually have a demo that shows this benchmarked against TensorFlow. And then we also can show some of our results on even larger data sets that we don't have time to run like during this presentation. But yeah, does that kind of answer your question? Yeah, I mean, so I guess that's kind of a hard question to answer just because there's so many industries that are using deep learning right now. One of the data sets we're going to give you a benchmark results for is like a recommendations data set from Amazon, which is like, so you have some information about like a user and products they've looked at in the past, and you want to predict which products are they most likely to look at and buy in the future. So that's an application. We can show you a demo just with like a basic like classifying MNIST, which is just classifying handwritten numbers and letters. So there's like a wide variety of things you can use this for. Because I guess it's not specific to any sort of problem. It's more specific to like a class of neural networks and like different machine learning models that you can use this apply to. So you can use it for any application of those. Does that answer your question? Okay.
In the following section, I will explain how do we speed up training and make our algorithm practical in practice. Yeah, so in the last section, Nick discussed the basics of our you are familiar with neural network, then you will realize that one critical bottleneck we have is that for every batch of data, we will need to figure out the hash value and figure out the corresponding active neurons. And if we recompute the hash values. Yeah, so let me get back to this again. So one critical bottleneck that you might have noticed is that in theory, for every batch of data, we need to recompute the hash values here to figure out which set of neurons are active and therefore needs to be computed. So, and as the network size grows, this cost of recomputing hash values becomes prohibitively expensive. So how do we solve this problem? It turns out that after each iteration, after we process each batch of data, only very few neurons are updated, and therefore the weight vectors change, and therefore which will lead to our hash code change. So that means that we do not have to always recompute our hash values after processing each batch of data. So in a naive implementation, we need to rebuild our hash tables for every batch of data. But then we made the observation that we can reuse all hash values. So what we do in practice is that we set up a hash table update schedule. And we made another observation that at the beginning of the training, the updates we make are bigger than when we are approaching towards the end of the training. So at the beginning of the training, we can update our hash values more frequently than towards the end of the training. And towards the end of the training, we can update our hash values rather infrequently. And in this way, we're able to speed up our algorithm to make it practical in practice. And what else can we do? What else can we do to further optimize our algorithm? It turns out that we can leverage the OpenMP library in C++ to get further speed up. So we are processing our training samples in a batch in parallel. And if you're familiar with the basic concepts of forward propagation and backward propagation in neural network, then another question that you might come up is that then if you are processing each data sample in parallel, then wouldn't they just overwrite each other's gradients? And the answer is yes, but that is OK in our scenario due to the extreme sparsity and randomness in our gradient updates. And this is thanks to the theory called Hogweld. And in the next few slides, I will give a brief introduction of Hogweld. And if you find this stuff too technical, then it's totally fine to skip the next two slides. So in a Hogweld-style parallelism, what we do is that we perform stochastic gradient descent over a batch of data in parallel. And we do not put any logs on our parallel SGD algorithm. That means that each thread is processing a data sample, and we are allowing them to overwrite each other's gradients. And because of this data race, the gradient that we read from one thread may not be the most current version. And in Hogweld theory, that is still OK. And how so? So because of the gradient sparsity, the updates will not interfere with each other too much. And in our particular application, for instance, in our application in recommendation models, we are only updating about 1% of the neurons. So even if we have multiple threads processing the data in parallel, then not many of them will update the same neuron. And although the updates can be old, there are experiments that show that there exists a certain bound on their age in practice. And also, the theory also shows that the algorithm can recover the behavior of stochastic gradient descent if certain conditions on processing time and the number of overlapping non-zeros are satisfied. So that is why we can further speed up our algorithm by processing all the data in a batch in parallel. So what are some other optimization opportunities? As you can see, until now, our algorithm is hardware agnostic. And the two optimizations that I talked about in the previous slides are also hardware agnostic. And of course, with the rise of domain-specific hardware, we can further leverage those hardwares to further speed up our code. And those hardware-dependent optimizations can be added directly on top of our algorithm. And this includes some cache optimization, some transferring huge pages for faster memory lookup. This includes vector processing. So if you use vector processing in the matrix multiplication in forward propagation and back propagation process, then we are able to speed up like matrix multiplication, just like how it is similar to how it is being sped up on GPUs. And we can also leverage techniques from software pipelining and prefetching to provide some more speed up. So this is the optimization that we made to make our algorithm that can run fast and be useful in practice. So, and here I would like to share this exciting news that we are collaborating with ThirdAI to help make our technology accessible to everyone. And ThirdAI is a company that is trying to democratize AI and and make AI work on your daily laptops and make it accessible to everyone. So if you can take out your phone and scan the QR code here, you will find more information about the package that we are developing called Boat. So in Boat, we develop a Python wrapper for our C++ package, and we actually also provide a script that you can take your TensorFlow or Keras model, and we will transform your models to run on our Boat engines on CPUs. And while some of you are scanning the QR code here, does any of you have any questions about the optimizations that I just discussed? Yes, please.
In your opinion, how large does the data set have to be before there's enough benefit by using different techniques? At some point, there may be diminishing returns given the extra work required.
Yes, that is a fantastic question. So the answer is, yeah, we like our models to be as big as possible. And the bigger our model gets, the more benefits you'll get from our method. And some of the current applications that we look at, we are looking at like billion parameter models, or at least models that have hundreds of millions of parameters, such as a lot of the recommendation text that Amazon and Facebook are currently using. And we are also looking into a lot of natural language processing text, and we are looking to extend our models to extend our package to support many different kinds of language models.
So what's the smallest large data set would you suggest for something like this?
So that also depends on the type of task that you are dealing with, and we are particularly good at tasks with wide output layers. So let's say you are trying to recommend a product to a user in Amazon, and Amazon might have millions of products, and we are really good at those.
I guess, sorry, to answer your question, I'd say it's not so much the data set as the model you're trying to train. And once you start getting layers that are the size of like tens or thousands of neurons, you can start seeing benefits from this type of acceleration.
Any more questions?
What is the fundamental step to enable you to do deep learning with CPUs? Is it the sparsity or the bottlenecks?
Yeah, exactly. It is the sparsity. And because of the sparsity, so one cost that we paid is that because we built all these hash tables, we will require more memory. And those memory, as we have discussed, GPU tend to have less memory, and CPU tend to have much bigger memory, and that's why we are running it on CPUs, because the hash tables allow us to do only very sparse computations, and we can only fit those hash tables on CPUs. And of course, CPUs is accessible to everyone, while GPUs are not. Sorry, can you? Do you mind also like ask a question here so that like it will get recorded, or it's fine. Or if you want to repeat your question.
I'm just wondering, like,
Oh, every time we rehash so every time a data sample comes in, we query the hash tables and fetch the corresponding active neurons from the hash table. So it is data dependent. So does that, yeah.
Who are the users of Bolt Engine? I went to the site.
Yeah, currently we are collaborating with, am I allowed?
You don't have to say specific company name. I know it might be confidential. I'm just saying, because, e-commerce website or, social media content generation or energy. I mean, I just wonder what kind of users. You don't have to tell me who are specific users.
For instance, yeah, we do a lot of, we have collaborators that work on recommendation engines, and we are trying to build this package into a general purpose deep learning engine on CPUs. So the end goal is that everyone who wants to train a deep neural network can use our package and to be able to train their networks on their personal laptops.
Oh, so you're saying this can be used by individuals instead of, I just wonder, is it a B2B or B2C? I'm assuming it's B2B, but I'm hearing you're also saying in the future anybody can use this? So
the individual and the corporates might have different use cases. So for our package, if you want to train really large models, then that's what the corporate want. But for individual users, you can also use our package to just train large models even on your CPU. And we are going to show that in the demo later, how you can do it.
It's primarily more business focused just because the people who are training like billion and trillion parameter models who would see like the biggest benefits from this technology
yeah,
are
I'm
business.
assuming this is a B2B product.
One question. Can you have a distributed implementation of this locally?
That is the next section.
Oh, okay. So, what I mean is not distributed like like data parallel, but can you have a hash table that's distributed along a cluster?
Yes, I'm going to discuss that in the following sections. Yes, I'm going to discuss that here. So the distributed paradigm that we use is actually model parallel. So we are sharding the models across the different GPUs and build like hash tables locally, if that's a quick answer. So yeah, in the next section, I will be talking about some of our efforts in making this package distributed on CPU clusters. So first of all, to motivate this problem a bit, why do you want to do distributed training on CPUs? So first, a lot of the cloud vendors have reported that the majority of the CPUs on cloud is sitting idle. So they have not been fully utilized. And usually what people do is that they train their models on large GPU clusters and perhaps performs inference on edge. And of course, because not everyone have access to GPU clusters, this is not affordable and accessible to everyone. So what we can do is, our package Bolt can enable distributed training on edge on any devices you have at any scales. So you can train this on a device as small as like Raspberry Pi, or you can go to commercial level multi-node clusters and train your large models there. And the second question that you might want to ask is, why is distributed training an interesting problem? Or why is it a hard problem that we might want to pursue? And here comes the two bottlenecks in distributed training on GPUs. The first is that GPU have very limited memory. So the newest model of the NVIDIA GPUs have about 32 gigabytes to 40 gigabytes of memory. And it's really hard to scale beyond that. Well, on CPUs, on a personal laptop, it's easy to have 500 gigabytes of memory, even terabytes of memory, and you could have essentially like unlimited memory when you have a cluster of multiple nodes. And the second bottleneck is that communication is slow in a distributed setting. So current solutions to reduce communication costs, such as quantization-based methods, are known to suffer in terms of accuracy. And as a result, if you perform multi-GPU training with full communication without the techniques such as quantization, then multi-GPU training is actually slower than single GPU training in many of the use cases. So this motivates us to start pondering about the question of whether we can do distributed training on CPUs. And the answer is yes. So we developed this distributed version of both to solve this problem. So first, as I discussed that CPUs have much larger memory. And both, we save 99% of the communication cost through LSH. And I will discuss later. And we will also show some result that distributed both is scalable in both multi-thread setting and multi-node setting. So how do we achieve that? So in distributed both, what we are doing is what we call a model parallel training. And model parallel training is when we sharded the model across the nodes we have, and each node will have a full copy of the data set. And in this setting, the activations and the gradients that we compute during the forward propagation and the back propagation process are communicated across nodes. And we were able to save like 99% of the communication since we only communicate the activations and gradients for active neurons. And here, the active neurons refer to the neurons that we retrieve from our hash table. And the weight vectors that connects like layers of neurons are stored locally, and they are never communicated across the nodes. So if we take a look at the diagram here, so here this is layer 1 and layer 2. So what we do is that we shard the model across nodes. So let's say we have n nodes. We shard our models across n nodes, and each node has a and each node has a full copy of the data set, and it process the data set and computed the activations or gradients depending on whether you're in the forward propagation process or the back propagation process. And then we use some collective communication library to gather our activations. So now each node will have a copy of the full activation. And these activations are fed into the next layer as its input. And for the second layer, we do the same thing. Here, we compute the activations locally, and then we gather the application across the activations or gradients across the nodes. And on the right-hand side, on the right-hand side of the diagram, this is also a diagram showing our hash table retrieval and activation computation process. And I want to stress again that here the activations that we compute are sparse activations. So we only retrieve about 1% of the neurons and only compute the activations for those 1% of the neurons. And here we'll show some results of our distributed boat. As I've said before, multi-GPU training is, in a lot of cases, slower than single GPU training when you perform full communication. And our distributed boat scales well in both multi-thread setting and multi-node setting. So if you fix the number of nodes you have and increase the number of threads that you use on each node, so that means if you look at the row, if you look at each row in this table and look horizontally, you can see we can achieve very significant speed up when we increase the number of threads on each node. And if you look vertically, that means that if you fix the number of threads that you have on each node and just deploy our method on more nodes, you can also see like very significant speed up. Yeah, and next I will hand it back to Nick to show you guys some cool demo of our boat package. Before that, any questions about the about our distributed package? Yes.
So I'm understanding most of this, sorry. But when you do these gather functions to bring together your different calculated hash tables,
Uh-huh.
you said that, of course, obviously you can have some collisions, but the data set is large enough that you can get away with it. What kind of logic do you use to decide what takes priority? Is first come, first served in the hash, or I mean, the gather function, or what?
So you mean, when you say collision, are you talking about the collision in the hash tables or the collision when we perform gradient updates? When we do the gradient updates. Oh yeah, so that you cannot control from our perspective is whatever that goes on in the computer, that you kind of just have to accept the fact that like your updates might be you might be updating on an older version of the gradient, but their theory and paper and experiments show that that does not affect our accuracy at all, and we will show in our results later that that does not that does not affect the accuracy.
What we see is that like for a lot of these types of things, you can get away with like 1% sparsity, like only 1% of the activations you're computing. And so the odds of like simultaneously updating the same component of the weight vector for the same neuron are incredibly slim. And so what we do is, just for the sake of speed, is you just kind of ignore that. And you say the odds of like, it's already an approximation algorithm. And so you can essentially get away, like what Patrick was saying, is our experiments show that it doesn't.
Oh, you can assume that the accuracy is the same.
Like exactly the same.
It's not exactly the same, but it's more or less the same. It cannot be identical because we are building like hash tables on different nodes, across different nodes. So and it's a randomized algorithm, so the accuracy is slightly different. So it's not identical, but it's like from accuracy concern, you can view it as like achieve the same level of accuracy.
Within a tiny amount, like there's a tiny delta just because it's a hash table, and so you get some like, you can fix random seeds and you can get the same accuracy, but if you don't, then you get like a tiny variation. Yes.
Yes, that is a great question. So the question says that the scaling studies do not scale linearly with nodes and thread. Is it due to all-gather where a large number of nodes and the communication in all-gather routine is considerably high, thereby limiting the linear scalability? Yes, for the all-gather operations, we cannot do multi-threading in all-gather in the all-gather function call. So we are performing. So whenever we are doing communication, we are processing it in a single thread, and that does limit the scalability of our algorithm. But comparing to the multi-GPU performance, I think we are already, this is already a very significant speed up.
The other thing you can look at here that's interesting is if you look at the diagonals of this chart, that's essentially the same number of cores. And you can see that like if you look here, you have like 2.12, 2.08, 2.26. You get, they're fairly similar. And so in some ways you can show that it's somewhat agnostic to how the cores are distributed. It's more about the number of cores, and you get similar speedups. Granted, it is slightly faster to like have them all on the same machine, just because that's always going to be faster when you don't have to communicate. But because of the sparsity, we can leverage that for really efficient communication, and so we get this really efficient scaling.
Is that a new question that pops up, or just? Okay, yeah. Answer live, yeah.
Cool.
Okay, next I will hand it over to Nick to show some cool demo of our package.
Yeah, so.
For the mic.
I'll just stand here. Okay, So what I'm going to do is, okay, demo. Yeah, so I'm just going to share my screen here. And then what we have is, okay, so we have two terminals. These are just on two separate machines, but they're identical machines, same memory, same cores, or whatever. And what we're going to do is here, so this is somewhat of a contrived example. What we're doing here is we're running MNIST. We're training MNIST, and we're just going to use a very simple network. So we're going to have the input layer. We're going to have one hidden layer with like 20,000 neurons, and we're going to have the output layer. Those of you who have done machine learning, you may say you do not need a layer that big to train MNIST, and I completely agree with you. This is more just to showcase that like on larger models, like the scaling that our algorithm can demonstrate, and on smaller models, I think this was a good question earlier. It doesn't, there are diminishing returns, and there also, it's kind of okay because if you have a really small model, it's already fast to train, you don't really need the acceleration. And so we're trying to show a larger model, also in limited amount of time because we only have a few minutes. And so this is kind of a good example. So, and then, so this is running with Bolt, and then here we can run, this is with TensorFlow. And so we can initialize it, and this is just going to train for 5 epochs. We can see here, oh, sorry, this might be kind of hard to see. I can zoom in, but on the left here, this is with Bolt. On the right here, this is with TensorFlow. And this is the exact same model, and this is just using here, I guess maybe it says somewhere, but this is with 1% sparsity on the hidden layer. And so it's already done training, and TensorFlow is still on the that epoch there. And then we can see here, so it's taking roughly 4 times longer. And then the one thing we are going to see here is actually with TensorFlow should be a little higher, and that's expected. And the reason we're okay with that is that this is an accelerator for training. And the idea is that if we can get close to the same accuracy in 4x less time, then we can always train like 1 epoch with TensorFlow or something and do like fully dense computations and get that last little bit of accuracy. But as long as we're within like the remote, like within a % or 2, it's really easy to come across that difference. But it's important is that we can get there significantly faster. And then that last little bit of convergence, that's easy. We could even run this for another couple epochs and it would still be done long before TensorFlow finishes. So yeah, TensorFlow got a little bit higher accuracy. Like I said, that's to be expected. And then just to kind of show, this is kind of what the code looks like too. So this is what the package is. And so just kind of emphasize too that we're not doing a ton of like fancy stuff. There are some extra configurations, but in general, it's like a fairly simple thing. The other thing we can show is what happens if we make this even bigger. So make this contrived example even more contrived. And let's go to like all the way up to 40,000 hidden units. Do the same thing with TensorFlow. And then we can just run the same code. And this is obviously going to take a bit longer because we just doubled the parameters in the model roughly. But we can still see that it's significantly faster with Bolt. There it's already done with the first epoch. And TensorFlow is still making progress on the first one. And so this is just kind of emblematic that when we have these larger layers, using sparsity, we can get these huge accelerations because we're doing significantly less computations. And yes, there's this overhead in the sense that we're doing these hash table lookups. It's not just purely computations, but the net effect is that we can still see a lot of benefit from this. I guess this is going to take a couple minutes to run because TensorFlow takes a while when you scale it to be much larger. Are there any questions about this or anything while we're waiting? Yes. This is not open source right now. This is proprietary. We have if you go to the website, there is like you can request like a trial version, but yeah, it is not open source yet. Yes. Oh, there's like a couple more slides. We wanted to show there are some bigger data sets that we don't have time to run during this demo, but we have some plots and stuff we just wanted to show you guys just to prove that we're not full of it, because obviously MNIST is like an easy example for those of you who've done machine learning stuff before, and it's not hard to get good accuracy. And so just to prove that we're not just like pulling a simple example out of our hat. But after that, otherwise, like, yeah, after that, then we're almost done. Then we'll have some time for questions. Yeah. Yeah, I would assume so. Everything else was the same. And I mean, like the accuracy, obviously you can get higher accuracy than MNIST. I just didn't want this to train for like a longer time. And so this is kind of a simple, like 5 epochs is a pretty short example. TensorFlow should be done soon. We can see here still though, we even get better speed up on the other one. It was 4 seconds per epoch with Bolt and 16 with TensorFlow. Now we're at like 7 or 8, or about 8, 7 or 8, and like 33, 34. So almost at 5 times the speed up. So we're also getting better scaling. I guess that's the other takeaway here. Okay, sorry about this. Maybe when I was making this demo, I should have thought about how long this was going to take to run. And there would just be like kind of an awkward silence. Is there a chat? Oh, sorry. Oh, yeah. Yes. Mm-hmm. Mm-hmm. Get to that in 1 second, actually. There's a couple slides I think will help explain it. Sorry, you had a question? Yeah. So this, yeah, we're just setting the sparsity in the layer to be 1%. So we're trying to roughly sample around 1%. We kind of set like a target. This is TensorFlow. This is just, TensorFlow doesn't have sparsity. It just is just all of the neurons, just doing dense computations. TensorFlow doesn't really have an equivalent though. So like, it's a fair comparison in the sense that what we're arguing is that using this sparsity and these techniques, you can get these types of speedups versus using like the standard, like this is like TensorFlow is very much the state of the art. On a lot of benchmarks, I think TensorFlow is usually the fastest thing. And so this is kind of a benchmark. This is like what the current state of the art is. And this is, we're saying this is like a kind of different algorithm and a different training engine, and that we can get the speed up. So like, I mean, is it a fair comparison? Maybe not. It depends on what you're, I guess you could argue it's not, but also there's not really something to compare it to because TensorFlow doesn't have an equivalent package.
I want to add that you can make TensorFlow to also train on 1% of the neurons, but then in that case you will do random sampling. And if you do random sampling, then that would hurt the accuracy by a lot. And the reason we can get to the same accuracy is because we use LSH to do some sort of adaptive sampling. Yeah. So yeah. The reason we can show like when you have time, you can also go home and try it out. You can use the same configuration and ask TensorFlow to sample uniformly 1% of the neurons, and the accuracy will be better.
Yeah.
There's a question in the chat.
Is there a question in the chat? Yeah, there's a question in the chat. Okay, so good question. This is just running on CPUs. We can actually, as I will show in a second, just because it's easy to compare to, but let me switch back to this and I will continue to answer that question a little bit more. So, okay, we have the demo. So that was our demo. Come on, why is it not? Okay, these are just videos of that same demo in case the demo did not work. I was a little bit worried. Or more like if something crashed or I couldn't log in, but that was all okay. So back to the other question, GPU, CPU. So for that demo, we're just using CPUs. What we see is that like on smaller models like that, our training engine is more efficient than like TensorFlow and PyTorch version on CPUs. But if the GPUs are still going to be faster for smaller models. However, if we get to larger models, so this is a 200 million parameter model, which in the big scheme of things is actually relatively small. If you think back to the graphs we showed at the beginning, That's like, a few years ago is when we were talking about hundreds of millions of parameters. Now we're talking about billions and trillions. Then we can actually start to beat GPU performance. So that's an NVIDIA A100 GPU. That's one of like the highest, one of the highest tiers. We have that. We have a laptop. And then here is like a bigger like kind of server GPU and an AMD and Intel one. And we see that comparatively, like TensorFlow on any of these things, Bolt is considerably faster. And what's even more interesting though is that even compared to a GPU, we're still getting that performance. So this is like a $10,000 NVIDIA GPU, and we can get slightly better performance on a laptop for this model using this training engine. And this is here just to show the convergence plot, just to also show like that when we say we're getting faster speed up, it's not because we're doing something silly and we're getting like 0.1% accuracy, but it's really fast. It's like we can converge to an equivalent accuracy, but in a fraction of the training time. Yeah, and so this is just some more convergence plots. And this one's also interesting. So this is just time and accuracy. And we have Bolt, TensorFlow CPU, TensorFlow GPU. But then what's even more interesting is that you can also look at the cost. And this is just if you were renting the space on like on Amazon, on AWS to train these models. Because you're training faster and you're using CPUs, which are just less expensive, you can also see that it's costing less to reach the same accuracy because you're using more efficient and more cost-effective hardware. So that's kind of the other interesting thing we wanted to touch base on. So I guess that kind of answers the question, I think, in terms of like, so the demo we showed, that was all CPUs, smaller model. Bigger models, we can get to this GPU level performance. And then one last thing, just kind of for fun, we can take the same thing and we can just make it bigger. So this is a 1.6 billion parameter model. And on this one CPU, we can train it much, much faster than TensorFlow. And if we use only 1 or 2 GPUs, it just runs out of memory. Like, it cannot store this model. So we have to go all the way up to 4 GPUs, which is still slower than our engine running on commodity like CPU thing. Like, we got this CPU server, I think like on average, each node comes out to be like $1,000. These are like each $10,000 GPUs. It takes 4 of them. And we're not getting the same accuracy because we can leverage this sparsity to do these computations more efficiently. And I think, yeah, I think, so that's the end. And so I guess now we have like a little under 10 minutes left. We can just kind of open it up to any questions you guys have. Anything else we're happy to talk about. Oh, there's another question in the chat. Let's start off here. Yes, this is basically, yeah, just fully, this is the Amazon 670K recommendation data set from Kaggle. Yeah, and we're just using a fully connected MLP. Super simple model.
Yeah, to give you more details, the input dimension is about 135,000, and the hidden layer that we use, we actually vary them. We vary from between 60 and 1,000, whatever you want, and then the output layer is dimension is 670,000.
Yeah. So it's a kind of large network. Yes. Go back. Why is it not working? Sorry, something's not working. There we go. This one? Sorry, that's a good question. I should have written that down ahead of time because I should have anticipated that. I think it's a couple 100 gigabytes of RAM. I guess kind of the big takeaway here is that, I guess, I don't remember the exact memory, and it varies a fair amount depending on the CPU. I think for this one that we're using, I think it's like a couple 100 gigabytes of RAM. But it's interesting to note that just like you can get these CPUs and it's easy to get to that level of memory, whereas GPUs, you need several GPUs to run. It's probably at least, yeah, it must be at least like 100 gigabytes just because 2 GPUs is running out of memory, so it's at least that much. Yeah, that's what basically, that's the limiting factor here with GPUs more than the compute. It's like largely what happens is what forces you to scale to multiple GPUs is just that you're running out of memory. You can't store a larger model than like 40 gigabytes or whatever of parameters, which isn't that many if you think about it. Yeah. You had a question? The sparsity? Oh, yeah, you totally can. It's a configurable parameter in the engine. Really, basically, if you think about it, sparsity 100% is just equivalent to having a fully dense model. And so it's kind of essentially a knob you can turn where the higher the sparsity is, the closer you're getting to essentially like what TensorFlow does, where you just compute everything. And the reason we kind of settle on 1%, I mean, partially because it's just kind of a nice round number, but also because we can get to the same accuracy. And so increasing the sparsity, all it does is it means more computation, so it's slower, but we're already getting to the accuracy we want, so there's no real reason to. So yeah. I do not know off the top of my head. It would probably be maybe a tiny bit more. For this data set, the best accuracy you can get is like, it's hard to get much more than what the accuracy you get, depending on the model and what you're doing, is somewhere between like 35 and maybe like 45% accuracy. And there's depending on what kind of like tricks you use for this, because it's like a simple example, we're not using any like fancy tricks and stuff, and so you get like around 35-40% accuracy depending. So you maybe get like a tiny bit more with a little more sparsity, but it wouldn't be like, you wouldn't double the accuracy, I guess. Yes? Or, sorry? Go? Yeah. Oh! Yes. Yeah. Yeah, exactly. And thanks for bringing that up. Sorry, I forgot to come back to your question. I meant to. Yeah, so this is kind of what I was thinking when I said that. I was like, here we have a laptop and here we have a $10,000 GPU and you can run the same model. And so that's what we mean, yeah, when we say democratizing is that we're just, I guess maybe a better term is just making it more accessible and less like prohibitive to the sense that you have to have this specialized hardware and specialized clusters to run it. Like, well, maybe there's like a better way, and that's like software acceleration. Sorry, I think there was another question. Yeah.
So there is this benchmark called ML Commons,
Mm-hmm.
and there is a recommendation benchmark that
DLRM?
yes, DLRM, and it's based on 1 terabyte data set. And in that benchmark, right now, GPU is leading like by a factor of
Yeah.
2. So I think you could improve it
Mm-hmm.
quite a lot.
Yeah, that's actually a good thing to talk about. That's one of the things we're working on too, is like trying to build, we have some ideas of how we can kind of build essentially a similar version of DLRM with our technology to kind of, because it's a huge model. I can't remember what the exact statistic is, but I think roughly like 75% of like a lot of like the models that are being trained on like AWS and stuff and like that are like being used in like industry are recommendation models. It's huge. I think the biggest three are probably recommendation, NLP, so natural language processing, and then like computer vision and based stuff. I think roughly, don't quote me on that, but I think that's generally to give you a sense of it. Mm-hmm. Mm-hmm. Thank you. That's really nice to hear. Yes, the terminology on these charts could probably be improved. Yeah, I think that's fair. And then, yeah, so yeah, I think that's fair. Yeah, and then I think kind of going off that too, one of the things we're also looking at is like applications for using like more edge devices and even like clusters of edge devices, or like a lot of times you have big cloud clusters, but a lot of it is inactive, and so can we use those like small bits of memory and CPU that that are like being underutilized on cloud clusters, and using algorithms like this to kind of in the background, because we have algorithms like Patrick was talking about with the distributed version of Bolt, where we have a way of using, like we can make use of low communication and just train these like distributed models on CPUs. And so could we do something like that on like basically inactive cloud regions, which is just, I mean, it's an energy efficient, it's cost efficient. If you invested all this money in this cluster and then, half the time it's just sitting around being unused, well, maybe there's a way you can take advantage of those resources and get more value out of it. Yeah.
So the probably noticed, but message passing interfaces way back in the day
Oh yeah.
use sparsity in order to be able to maximize the throughput, right?
Mm-hmm.
Yeah, all sorts of algorithms for nested parsing nodes. But but I wonder if just how well the model would scale if you started using if you could delay even further the passing of messages between your nodes, like using a high throughput compute model, right?
Interesting.
Like the Condor system, which has a very similar call-out speed to using underutilized CPUs.
That's a really interesting idea. Yeah. Yeah, a big reason for using MPI is honestly just the convenience. It's easy to kind of test and run those things on it.
When you start talking about linear scale, right?
Yeah.
Like you can bring 1,000 CPUs together.
Yeah, absolutely. And the other thing that's cool about this too is just what we're excited about is, we already see that we can go out of memory on like one CPU, we can go out of memory for like up to like a couple of GPUs. But we can even start bringing in more CPUs, and we can get scaling. And so we're kind of starting to think of like, what are the models that no one's tried to train before because they just use too much memory on GPU? Because now we kind of, it's a different problem. Like some of those problems that GPUs run into, which is largely memory bound, you can start to think, well, that's actually not an issue anymore. And what kind of doors does that open for us? Yes. Oh, good question. Actually, it wasn't even a CNN. We were just using a fully connected network because it's MNIST. It's pretty easy. You don't need to use, you can use a CNN. So for right now, we're doing mostly, we haven't done like LSTMs and stuff yet. That's kind of the next area of research is we kind of like, what other types of models we can extend this to. I think one of our focus is gonna be like on like NLP stuff, and image stuff, and vision stuff, just because those are two very big areas. So far, we've been focused more on like recommendation, just because it works very well with the technology, and it's a big problem, like open problem. But yeah, that's a good question. So I think that's kind of like the next iteration of this is like, how can we apply it to other model types? Sorry.
Yeah, and to add on to Nick's point, over the years, we've seen this trend that LSTM, like the natural language processing, are gradually being replaced by attention. And now people are seeing that you can use fully connected networks with support to gradually maybe even replace attention. So we're seeing this kind of convergence of the model, and we are working on supporting that this model can maybe more probabilistic. But right now, the fully connected network is already doing a lot.
And there was an interesting paper in the last year or two, I think called like Reformer, that was about using locality sensitive hashing to do attention in transformers. So there's interesting things like that that are out there. Yeah. So I guess we're out of time, but I mean, we're happy to stay and answer questions if there's anything. Thank you all for coming. I mean, mostly we're all there. Henry, who was presenting earlier, works there. We have a few other people. We have a lot of people from our lab are here. You guys can wave. Okay, maybe they're shy. They won't wave. Mostly, so like I'm an undergraduate. Alan and Patrick are masters. Henry's another undergraduate. Yeah, we have PhD, obviously professor. And then, I don't know, mostly CS, electrical engineering, math. Thank you. Thank you, everybody.